My name is Sasha, and I'm from the University of Tokyo. This paper was co-written by this Masaki Kondo and Hiroshi Mizuno, and jointly funded by the GSPS and JC Press. Our research deals with exploring a distributed reinforcement learning approach to accelerate the learning of power management policies for energy harvesting wireless sensor nodes. Now, energy harvesting wireless sensor nodes are very attractive solution for the IoT infrastructure. And one of the reasons that is because we can expect autonomous and perpetual operation from them. Of course, that's contingent upon a very adaptive and intelligent power management policy that can work with a very diverse and unpredictable power source, as well as it should be scalable to billions and trillions of different sensor nodes that we can expect from the IoT in the future. And since we're only concerned with the power or the energy management aspect of this, we abstract away the energy of the wireless sensor node and look at only its power characteristics. So we look at a very simplified system called the ENORL, Energy Neutral Operation Reinforcement Learning System. The sensor nodes is simply an energy consuming device whose energy consumption is dependent on the duty cycle, powered by a battery which in turn is charged by a solar cell. Now, the duty cycle is determined by adaptive power management. And the point of the adaptive power manager's objective is to achieve energy neutral operation, which is basically you want the amount of energy consumed to be equal to the amount of energy harvested. So if you look at this figure over here, we would probably want the energy, the battery profile, these are the battery profile, to be somewhere around like the green curve, where it doesn't touch the extremities, meaning you don't want it to go to 100% or 0%. We want to minimize the instances of these overflows in which the battery goes to 100%, because this means that any excess harvested energy will be wasted. And we obviously don't want the battery to go down to 0%, because that means the sensor node is out of operation. So the energy neutral operation objective goes down to minimizing this. And since we want to consume all of the energy that we harvest, we also want to maximize the duty cycle and make sure the sensor node is always on. To this end, we use the reinforcement learning method. Well, reinforcement learning is a machine learning technique best suited for sequential decision-making tasks. And we model this duty cycle determination as a Markov decision process. So in this RL paradigm, we have an agent that interacts with its environment through some actions, in this case the duty cycle. And then once it takes a particular action, the environment reacts to it by taking it to a different state and gives a reward as feedback as to say how good that particular action was at that particular state. And once it learns that, gets that reward signal, it learns to better refine its policy to get a better understanding of what to do next time. So the point of reinforcement learning is to learn this goodness of an action at a particular state. Now, how do we learn this goodness? It's just by doing lots of trials and errors. And to make sure we can generalize across different states and actions, we use a deep reinforcement learning approach in which we combine a neural network with the reinforcement learning paradigm and put them together. So basically we have a neural network. In this case, we use this architecture, the dueling double DQ network proposed by Wang in 2015. So basically it takes the state and looks at all the actions and to determine how good each action was. Now, the point is, since we're starting from estimates, we're making better guesses based on our initial random guess. We don't really know if the goodness of each action is accurate enough. So at times we have to take random actions, put some noise into the action space so that we kind of explore all of the state space. And for that we do something called epsilon gradient, basically, which means with the probability epsilon, you don't take the best action, you just take random action. So we implemented this and we got a pretty good result, very encouraging result. You can see this is the power management policy for the RL system I just described. The battery level is well within the desirable range. The blue duty cycles adapt accordingly if it's a sunny day or if it's not a very sunny day. during the day and at night. So it's working very nice. We use this state space and action space. Basically, those 4 pieces of information. We use discrete cycles. So to see how good our power management policy worked out, we need a performance metric. And for that, we use energy neutral operation. And there is no strict definition for what energy neutral operation is. So we define it as in a span of 365 days, consecutive 365 days, if you have less than 24 violations. So less than 24 times when your battery goes down to 0% or goes up to 100%, then energy neutral operation is achieved, which I think is a pretty strict metric, a pretty strict standard. So it says that we take about 10 years worth of simulation, 10 years worth of data to train this network. And during its training, of course, it's going to make a lot of mistakes. And the amount of mistakes it makes results to about 2 years worth of inefficient operations, maybe downtimes, or it was almost 2 years worth. But after it trains, when we run it from 1995 to 2018, so that's almost like 124 years worth of we run it through. There are no violations, it works perfectly. This is like as optimal as you could get. So while this is very encouraging, it is still unrealistic because you can't wait 10 years for your node to train itself. By the time your node is probably dead. So we're looking at ways to accelerate this training. Because reinforcement learning is notoriously sample inefficient. So we're looking at ways to look how to make this faster. Can we do it in a more realistic way? So in our case, for this very particular case, we have the advantage that we have multiple nodes in the network. And these nodes are interacting simultaneously with the environment. So is there a way we can leverage this infrastructure and learn faster and scale this learning? And the answer is yes, we can. What we can do is, how about we collect all the experiences from all these different nodes together and pull them together, learn a more robust, more intelligent policy, and give them back with the nodes so that they work smarter. So this is the basic theme behind our research in the paper. And so for this end, we use the distributed learning, reinforcement learning method. So we have one server, and then 10 different nodes operating in 10 different environments. And these nodes interact with its environment at its particular time interval. It gives back its experiences, it uploads it back to the central server. And the server, since it's a computationally very powerful machine, it can learn a really robust policy and send it back to these nodes. So this is the basic idea of what we're trying to do. Now, we proposed 4 or 5 different algorithms. The first one is the distributed ENO, which just uses a naive distributed RL approach that I just described. However, we observed that even with the distributed approach, the state space is not fully explored. We don't see all the different variations that the environment can give to the node. So it resulted in non-robust policy. So we decided, okay, how about we make sure that we explore all parts of the state space? And we do that by partitioning the state space for each node. So like node 1 looks at this part, node 2 looks at this part. So maybe we can get a better policy. And it does, but it comes at a risk of more mistakes because some nodes are in a very more dangerous space than the others. And then we decided, okay, if that's kind of unfair to the nodes, so how about we uniformly distribute the risk of exploration among the different nodes? So we proposed another algorithm called safety ENO. And while it did decrease the number of mistakes made, it didn't get the best performance. I mean, better performance than the first 2 ones, but not still the optimal. And we realized that that's because there's a trade-off between the number of mistakes you make, the learning penalty, and the performance you get, or the operation penalty. So if we could dynamically adjust it so that we get the absolute minima, so that we can get the best result, best of both worlds, it would be really cool. And to do that, we use adaptive, that adaptively changes the exploration rate so that you get the best of both worlds. In a tabular form, this is our comparative results. The single agent, the non-distributed one, took about 10 years to learn, makes about 17,000 mistakes. Once you go distributed with 10 different nodes, we decrease that by almost 17 times, and we make far less mistakes, almost half. but it's not as robust. We make more mistakes during the testing part. So what this shows, it's not as robust. So when we partition the state space with PE node, we were able to decrease the learning time, but the number of mistakes it made during learning increased because some nodes were at a more dangerous place than others. But in the end, the policy that was learned was pretty good. I mean, better than the distributed one. By uniformly distributing the risk, we were further able to decrease the learning time and the number of mistakes we made, and got better performance. But still, it is not as optimal as PEN. So then we realized there's a trade-off there. So then when we go to the adaptive method, we can see that there's a trade-off between the number of mistakes you make and the performance you get. So adaptive method learns in a shorter amount of time, makes more mistakes, but is a better performer than SE. So this is you can do a trade-off here. The picture just shows the same thing again. So this is a log scale. So a single agent takes about 537 weeks. With our method, we can go down to 10 weeks, which is a more feasible solution. You don't need to wait 10 years for your node to learn. You can do it within 2-3 months. It shows the number of mistakes you make, the node makes. We can see that the safe method, the SENO, the red one, has the least number of downtime. So when the battery goes down to 0, this is during learning. And the adaptive method has a little more, but the most is from the partition leader because it makes the most mistakes. So I talked a lot about partitioning the state space, and I would like to go more into detail how we actually partition the state space, because that is, I think, the crux, one of the main insights we have. For this particular problem, there is a direct correlation between the duty cycle you choose and the battery level you end up at. So if you look at this figure here, it's just an extreme example. The red points are the state space points visited by a agent that explores using high duty cycle. Whereas the blue points are the points in the state space visited by an agent that uses a low duty cycle. And we can see there's a very clear partitioning here. So this is obviously an extreme case, but if we can go somewhere in the middle and change the state space for different nodes, maybe we can get a better exploration strategy. We can explore more in the same amount of time. And that is exactly what we did. We biased the duty cycles to explore different states for different nodes. And then so this figure shows it even better. This shows the state space. If we just take the battery state values and the amount of harvested energy values, that's the state space you can get. With the naive distributed method, there is very little spread. Not all points are explored. If you partition it using our method, you see that there's a bit more exploration. If you play safer, and this was a very pleasant surprise, that if you actually distribute the risk, you get to explore more. And then with an adaptive dynamic trade-off, that is the most spread and obviously the best performance. So this is all about how we learn. So let's see how it actually works. So this we ran the trained agent from 1995 to 2018. This is a sample year from 2002 for the weather in Tokyo. And we see that the battery levels, we start from about 50%, and it's working pretty fine. It's staying within the desired levels. It doesn't go all the way to 100%. It doesn't drop to 0%. And it goes all the way. It works during the winter and the summer, and it's pretty nice. To go more into detail how it adapts to different seasons, let's look at these two figures. This one shows the one for 10 days in summer and for 10 days in winter. During the summer, you can see the gray lights show how much energy is being harvested. And we said it's pretty high, except for maybe the 234th day and the 238th day. And in spite of that, the duty cycles are maximized and the battery level stays fairly constant within the required range. During the winter, the opposite happens. So usually the days have very low solar energy. But there are some days when you do get high energy and the duty cycles are maximized on those days. So the same power management policy is intelligently adapting itself methods. So in conclusion, we used distributed reinforcement learning to accelerate the learning of power management policies. By simply partitioning, we were able to get better performance, but we made more mistakes. To uniformly distribute this risk of exploration, we were able to trade off some, we were able to get better results, but with some trade-off in performance loss. And by dynamically adjusting this trade-off, we were able to get really good results. Thank you for listening. Any questions?